Welcome to Speaker Night at the David Dunlap Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton, and I am delighted to be your host for tonight's lecture, along with the DDO Outreach Coordinator, Quentin Wayrich. Tonight, we are here at the David Dunlap Observatory, hoping that the weather holds out and the skies stay clear so that we can bring you some live views later this evening. But before that, I wanted to welcome you, our viewers, to tonight's lecture. Please take a moment to say hello in the YouTube chat if you haven't done so already, and tell us where you're joining us from. This helps us to make sure that our technology is working properly. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The observatory is home to Canada's largest optical telescope, which is right here behind me. Tonight, I'm delighted to be operating the telescope myself, and again, hoping for clear skies, hoping those clouds hold off. We would like to start tonight's event by acknowledging that the David Dunlap Observatory here in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge that this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. Tonight, it is my great pleasure to introduce our speaker, Julie Claveau. Julie Claveau graduated with a degree in physics and astronomy and is currently Program Officer for Smart Earth at the Canadian Space Agency, or CSA. In this role, she is involved in conducting studies and awarding contracts and grants to Canadian industries and researchers who are interested in developing novel applications using Earth observation data. As an advocate for diversity and inclusion, she is also co-chair of the CSA Women in STEM Committee. Her previous roles include Program Scientist in Space Astronomy, where she acted as Deputy Mission Manager for the James Webb Space Telescope, Earth Observation Mission Planner for the RADARSAT-2 mission, and Project Manager for the RADARSAT-1 Open Data Project. As Deputy Mission Manager for the JWST, she was responsible for negotiating, developing and maintaining strategic partnerships with international partners such as NASA and ESA, and for managing JWST-related contracts for hardware and software. She was also involved in securing JWST observation time for Canadian astronomers and creating and awarding research grants. Ms. Claveau loves talking about space, sharing her story, and mentoring young professionals. She currently supports organizations like Skype a Scientist, SEDs Canada, and Zenith Pathways. She is also involved with the United Nations Office for Outer Space Affairs, Space for Women initiative. Her passion for space started at a young age, stargazing for hours, which then followed with a passion for the physics of space and our place in the universe. Tonight, Julie Claveau's lecture is titled Canada's Role in the James Webb Space Telescope Mission, and looks at the journey involved in bringing this space research mission from concept to launch. If you have any questions for our speaker, please post them in the YouTube chat. Julie will have time to take your questions at the end of her talk. Please join me now in welcoming Julie Claveau.
Thank you so much, Denise, and thank you to Rask Toronto and DDO for having me today. And thank you for all the people that are here today listening in. I'm really excited to talk to you about Canada's role in the James Webb Space Telescope. So, as Denise mentioned, James Webb Space Telescope, we often call it JWST and sometimes Webb. So, in my presentation, I might refer to either. And I think everybody knows that we're all, not just the scientists and the project management team, but the world is super excited about this new observatory. It's already changing every field of astrophysics and our view of the universe. As you know, it was launched on December 25th of 2021, so just recently, on an Ariane 5 rocket from ESA in French Guiana, and commissioning actually ended in July 2022, and we've started getting some really amazing images. The mission is a collaboration between NASA, ESA, CSA, and it's been more than 25 years in the making to get this telescope into space. And it included governments, industries, universities from all around the world. More than 1,000 people in 17 different countries. So it's really like a worldwide effort from various backgrounds, engineering and science, obviously, but there's also administration, communications, finance, and I'm forgetting a whole bunch of fields that I'm sure you can think of, but there's really every single field involved in this mission. Usually, the missions that we launch in space, their expected lifetime is 5 years of nominal operations. But right now, I think we're expecting at least 10 to 15 years because the launch went so well. And just to give you a ballpark number, Hubble is actually around 31 years old right now. So we could, if everything goes well, even look far beyond that. So we often hear about Webb being Hubble's successor, but it's actually pretty different. First of all, as you can see in the image here, JWST is much bigger. It has a 6.5 meter mirror, and Hubble is 2.5 meters. The mirror on Webb is actually on the outside, whereas Hubble is on the inside. And Webb's mirror is made out of beryllium and gold coated. And the gold coating optimizes the light reflection. And whereas, basic silver and aluminum mirrors would reflect about 85 to 95%, I would say, of infrared light, gold actually reflects about 99%, so much more efficient. Obviously, the bigger the mirror, like on James Webb, the more light it will capture, which means that we're going to have much higher resolution, which we do, and I'm sure you've seen some of the images already, and fainter things. We can also see fainter things that are much further away. Webb actually looks in the infrared light, which allows us to see I'll show it in the next slide, but it allows us to see through gas, cosmic dust, and also very, very far away. But Hubble actually looked in the optical, is an optical telescope, and it looks in the visible light, much like our eyes would see. And JWST has a sun shield that you can see here. It has like 5 layers. That's actually to protect it from the sun's radiation. So why use infrared? Well, first of all, optics is like our eyes, right? So see visible light, which is what Hubble would see. And infrared actually allows us to see through dust, gas, or as you can see in the image in the top, in the bottom right, sorry, through a garbage bag. We see the heat of an object or a person. In this case, in the image below, you'd see his arm, the person's arm through the bag, right? So that means that we're going to be able to see through dust and through gas as well. We're also going to be able to see the beginning of the universe. As I said before, by looking at the light of stars, we can see in the past. And some of that light that we're seeing may not even exist anymore, some of those stars that we're looking at, right? So for example, the sun's light takes about 8 minutes to get to us because light travels about 300 kilometers per second. So with Webb and infrared, we'll be able to look really, really, really far into the past, or we are looking really, really far into the past because light takes a really long time to travel to us. So we're actually going to be able to see really, really close to the beginning of the universe. And we're also going to be able to see stars being born in nebulas. And I'm going to show you some images later on in the presentation showing you exactly that. So let's look at the launch. I'm sure a lot of you have already seen it, but I always find it fascinating to look back at it. So let's have a look at a quick video. There's no sound to the video, but I'm going to talk you through the different actions that happen. So as I said before, it launched on December 25th. And the first thing that happens is the liquid fuel engine turns on and there's ignition of the two solid rockets on both sides. When it lifts off, there's lots of shaking, and there was actually shake tests that were done way before launch to make sure that nothing would be broken on the telescope. So lots of shaking. And as the rocket gets the maximum speed, the empty solid rocket motors will fall off. You'll see this in a couple of seconds. And as the rocket reaches the upper atmosphere, there's no protection is needed anymore. So the payload fairing falls away. So that's the nose cone protection, and that actually protects the payload from the pressure and heating during launch. As the first stage finishes fuel, it shuts down. It's empty, so it separates from the upper stage, and then the upper stage motor will ignite, and the trip to its orbit continues. So the telescope is now exposed, right? Because the fairing fell off, and it's really delicate. And to protect it from the sun's heat, to avoid overheating and damage, there's a series of oscillations from left to right that's done just to protect the telescope. And then once everything is clear, Webb will separate it from the launcher's second stage, and then it continues on its path to its orbit, to its final orbit. So let's have a look at the orbit. Webb is actually in a solar orbit, so it's the yellow line that you're seeing right now. And we call that L2, or Lagrange point 2. It's 1.5 million kilometers away from Earth. So if something breaks, we can't fix it. If hardware breaks, there's no servicing at that orbit. So L2, Lagrange point 2, is a semi-stable orbit around the Sun-Earth system. So as you can see, it's orbiting, and it's always aligned with the Sun and the Earth. And that semi-stable orbit, it's because the gravitational pull of the Sun and the Earth is equal to the centrifugal force required for Webb to move with them. And like I said, it's always in line with the Earth and the Sun, because the sun shield from Webb, you can see it right now, the mirror is facing towards us, and the shield is always facing the Sun-Earth system. And that's to eliminate all radiation from, or as much as possible, from the Sun and the Earth, because the Earth-Moon system also emits radiation. So that's why it's always in line with both, because if it was just in line with Earth but not in line with the Sun, then it wouldn't be protected from all of the radiation. Hubble is actually not Webb, but Hubble, just to give you a bit of an understanding of the orbits. Hubble is actually in a low Earth orbit at 540 kilometers around the Earth. So it's actually orbiting the Earth. It's a very, very different orbit, and it's lower than the Moon, obviously. The International Space Station orbits even lower than Hubble at 418 kilometers altitude. So they can be serviced by space shuttles, but Webb can't. Another thing that I would like to mention is that there's two sources of power on Webb. There's a solar panel, which is solar panel solar power from the solar panel, and that's to power the science instruments on board. But there is also fuel, and that's for orbit corrections. As you can see, it's going around the sun, but it's also doing a small circular orbit around the Lagrange point too. So oftentimes we have to do slight corrections just to make sure that it stays in the correct orbit. So let's have a look at the different parts of Webb. So there's the sun shield, which is the size of a tennis court. It's absolutely huge. And that, like I said before, protects the instruments from the heat of the sun. Without it, the images that we would take with Webb would just be one big blob of light. So we wouldn't see anything. Very, very important. It's coated in aluminum and silicone to reflect the sun's heat back into space. And it gives it that kind of purple color. That's actually the real color. And it's to toughen the shield and help it reflect heat. The difference in temperature from the sun-facing side to the side of the science instruments is actually really, really big. There's this the sun-facing side is at 85 degrees Celsius, I believe, and the sky-facing side, where the mirror and the science instruments are, is at minus 233 degrees Celsius. And there's insulation between each of the 5 layers of the sun shield to reduce even more the heat that's going in. And each layer of that sun shield is as thin as a human hair. So very, very, very thin. So it can be damaged by micrometeorites, which already no, it wasn't that. It was something that hit the mirror, I think, a micrometeorite, and everything is fine. Like, it wasn't major. So if you heard about that, nothing to worry about. And it's actually equivalent to the sun shield, like the heat protection that it gives the science instruments in the mirror, is actually an SPF. It's equivalent to an SPF factor of, I think, 1 million. So it's really, really, really big. And as you know, and I'll show this in the next slide, Webb was folded when we launched it into space to fit in the fairing of the rocket. And there was actually like around, I think, 140 release mechanisms. There's 70 hinges assemblies, 400 pulleys, I think something like 100, maybe less. I think it's less than 100 cables, and 8 deployment motors. So it was really complex to fold it and then have all those mechanisms kind of deploy on their own once into space. It's really, really fascinating how the team got it done. Then there's the Earth pointing antenna. And the Earth pointing antenna is actually for communication with the Earth. So, when we need to send codes up to fix software, there's continuous communications with JWST, even like to send data back to Earth on the ground stations. There's 3 large antennas on the ground stations, and one's located in Australia, another one in Spain, and there's another one in California, I believe. So that's to receive data and also to send software fixes up. There's routine operations, like I said, sending commands up, and I think it's twice per day, maybe once per day. Anyways, this constant communication with the satellite, and we use the Deep Space Network, so DSN, to do that. Then there's the momentum flap, which balances the solar pressure on the sun shield, sort of like I would say like a sail in a sailboat. So it balances the solar pressure. And then there's the star trackers. It's a small telescope that uses star patterns to target the observatory in the right direction. And there's the mirrors. There's a secondary and the primary mirror, and those are to take the pictures, the images. And then there's the ISIM, the Integrated Science Instrument Module. Oh, it's right there in the image. And all the instruments for science are here, and we'll talk about them later. Then the last item I'm going to talk about is the spacecraft bus, which supports functions for operations like propulsion, communication, electrical power, and data handling. So let's have a look at how Webb unfolded in space once it was in its not once it was in its orbit, but on its way to its orbit, sorry. So 30 minutes after launch, or about, well, maybe 30 minutes, the solar array was deployed. So that's the solar panels for solar power. And then 2 hours after launch, the antenna was deployed. So this is the small thing at the bottom. 3 days after launch, the sun shield pallets were deployed on both sides. And then on day 4, the tower assembly lifted up. Then on day 5, the momentum flap was deployed, and the sun shield membrane cover was were released. Then on day 6, the sun shield mid boom was deployed. And on day 7, the sun shield membranes tightened. So we'll see that in a few seconds. There you go. And then on day 10, after launch, the secondary mirror support structure deployed. And then on day 11, the aft AFT radiator was deployed. Day 12 and 13 is the primary mirror wings deployment. So both sides of the hexagon shape were deployed. And then day 29, so a month after it was launched, it was inserted into its Lagrange point 2 orbit. And then the instruments, the science instruments, were turned on after the telescope had cooled enough. And then we did optics checks, alignment, calibration, and science operations 6 months after launch. So Webb has 4 main science objectives. The first is other worlds. So this is atmosphere of extrasolar planets, and maybe even find building blocks of life elsewhere in the universe, which would be really cool to find habitable planets. And we're also looking at other planetary systems to study. That's also going to study, we're looking at other planetary systems, and we're also going to study, as you've seen, we took images of Neptune, I believe, and Jupiter, if I remember correctly. So we're also going to study objects in our own solar system. So some of the key questions here for the other worlds mission objective. So how are the building blocks of planets assembled? We're also going to look at what are the components of stellar disks that give rise to planetary systems, and how do planets reach their final orbits. Like I said, we could find habitable planets, which is super exciting. Essentially, they're exoplanets. We call them exoplanets. And the way that we would discover them, or that we do discover them, is when they pass in front, like in transit in front of their host star. We use transit spectroscopy to detect things like water, carbon dioxide, methane in the planet's atmosphere. So as the planet passes between us and its star, there's actually, it dims the light. Obviously, it's in front, right? So it dims the light of its star, and then the starlight will pass through its atmosphere. And that way we can detect like the different elements that are in the atmosphere. Then another mission objective is this life cycle of stars. So essentially, we're able to see through massive clouds of dust, like nebulas, where stars and planetary systems are being born. And some key questions here are how do clouds of gas and dust collapse to form stars? Why do most stars form in groups and not alone by themselves in the middle of nowhere? And exactly how do planetary systems form? The third mission objective is early universe. And like I mentioned before, Webb is kind of like a time machine, which is super cool. And it has infrared vision that's going to look back over 13.5 billion years to see the first stars and galaxies forming out of the darkness of the very, very early universe. For example, in the reionization period, which is a process that caused protons and neutrons to start combining into ionized atoms of neutral hydrogen and eventually helium. And when baryonic matter like hydrogen and helium formed and stars and galaxies. So some key questions here for the early universe: when exactly and how did reionization occur? When did it start? When did it occur? What sources caused reionization? Why did all of a sudden did atoms reionize? And what are the first galaxies? How did the first stars and galaxies differ from those of today? So those are the main questions. Then mission objective number 4 is galaxies over time. So we want to compare different kinds of galaxies over time, right? The faintest and earliest galaxies to get today's spirals and elliptical galaxies. And that's going to help us understand how galaxies assemble over billions of years. So some of the key questions: how are galaxies formed? What gives them their shape? What's the influence of the central black hole to its host galaxies? And what happens when galaxies collide together or join together? So those are some of the key questions. So we're going to go into the science instruments. So there's 4 different science instruments, but I'm probably going to be talking about the ones that Canada provided. So we provided 2 instruments: fine guidance sensor (FGS) and the near infrared imager and slitless spectrograph. And we call that NIRIS. And actually, these were done through, I want to say, 2 contracts. Those are the ones that I know. So there was an engineering contract with a team at Honeywell who built the hardware, and then there's a scientific team at Université de Montréal, led by Université de Montréal, sorry, who built the software to go with the hardware. So those were the 2 main contracts. Obviously, there are, these are multidisciplinary teams, and they have partners in different industries, different universities, different government entities like NRC, Hertzberg. So I'm not going to enumerate them all, but they have lots of different partners. And so this was done in collaboration. And there's some of the United States as well that helped out. So FGS, the fine guidance sensor, is actually like a really critical instrument to the James Webb Space Telescope because it allows it to determine its own position in space, to locate and track its celestial targets, and to remain steadily on target. So to always follow its target with really, really high precision. And just to give you a bit of an idea of how accurate it is, it's an accuracy of 1/1,000,000th of a degree, which is the equivalent of seeing a baby's hair 1 kilometer away. So that's crazy precision. And then the nearest instrument is going to enable scientists to determine the composition of exoplanet atmospheres, so potentially to detect, to find habitable planets, or to find the building blocks of life elsewhere in the universe. Okay, so we provided those two pieces of instruments to the mission, and in return, Canadian scientists received we secured at least a minimum of 5% observation time using Webb. So what that means is when our researchers apply for grant for observation times, not grants, sorry, observation time directly at NASA and SDSCI, there's 5% of that time that must go to Canadian investigators. So, Canadian researchers. And, there's nothing that says that above that, they can't, if their science is really relevant and is going to, really have a tremendous impact on science, then obviously we can have more than 5%. But at the very least, we negotiated to have 5%. And I know of scientists that are part of the early release science. So that's currently going on. And then we also got 450 hours of observation time for guaranteed time observations. And that's for our scientific team that wrote the software for the instruments that we provided to the mission. And on top of that, we also have what I was telling you before, the 5% of observation time. So that's the general observations program. Okay, so here, like, I've got just a few slides of images because I think they're really cool. So just to see the improvements over time with different telescopes at approximately the same wavelength. So this is the same region of the sky. So you see WISE here on the left, then Spitzer, and then JWST. You can see how crazy the resolution is for Webb, and the technology has evolved so much that we're able to have that high of a resolution. It's absolutely amazing. So these are the first images which were announced. I believe this was in June. Yeah, July. Can't remember, July, June. Yeah, it was in June or July. Anyways, around that time. You've probably seen them already, but for those who haven't, I'm going to explain what they are briefly. So on the top left is the Carina Nebula. And this is actually my favorite image because it's so bright and colorful. I know it's just the editing, but still it looks pretty. I like it. So it looks like mountains and valleys speckled with glittering stars. It's so beautiful. But it's actually the edge of a nearby young star forming region we call NGC 3324. And I've heard it called cosmic cliffs as well. And it's in the Carina Nebula. So that's what we're looking at. So it's the edge of a giant gas cavity with an NGC 3324. And the tallest peaks in this image are about 7 light years high. So it's huge. The cavernous area is being carved from the nebula by the intense ultraviolet radiation. And stellar winds from extremely massive hot young stars located in the center of the bubble are located in the bubble above the area shown in this image. On the top right, you have the Southern Ring Nebula. So this is really interesting. The dimmer star at the center of the scene has been sending out rings of gas and dust for thousands of years in all directions. And Webb revealed for the first time that this star was cloaked in dust. Webb is going to allow astronomers to learn more about planetary nebula like this one, where clouds of gas and dust are expelled by dying stars. And then there's Stephan's quintet on the bottom left. So essentially, it's a group of 5 galaxies. This image is actually Webb's largest image to date. It's a mosaic of about 1,000 separate image files. So I can't even imagine the work that must have taken to put everything back into place. This is really amazing. It's equivalent, like the height and the width is equivalent to about 1/5 of the moon's diameter. So it is huge. The information from Webb is going to give us new insights into how galactic interactions may have driven galaxy evolution in the early universe. And with its extremely high spatial resolution, like I was mentioning in previous slides, we can see new details like clusters of millions of young stars and regions of the new star birth. The one in the middle at the bottom is WASP 96b, and you can see the spectrum of hot gas giant exoplanet that I just mentioned. It's WASP 96b, and the peaks in the graph actually show the signature of water with evidence for of clouds and haze in its surrounding atmosphere. We know this because of the tiny decrease in the brightness of a specific light color as the planet passes between us and its star. So transit spectroscopy, like I was mentioning before. Whoops, one bit ahead. And in 2013, Hubble actually analyzed the very first detection of water. And there's been many since then, but none of them are as detailed as this. So this is really a gigantic leap forward in finding habitable planets beyond Earth. And then there's SMACS 0723. This is the deepest and sharpest infrared image of the distant universe to date. We call it Webb's first deep field image, and it shows the galaxy cluster SMACS 0723. There's literally thousands of galaxies here, like thousands and thousands of galaxies, some that are gravitationally lensed that are behind other galaxies. And if you take the high resolution image and you can zoom in like a lot and see even more galaxies than you see now. And just to give you an idea of its size, it's literally the size of a grain of sand held at arm's length. Like it's a teeny tiny part of the universe. So um I'm kind of it makes me wonder, like, if it's the size of a grain of salt, how many galaxies are there in the universe? So there's a lot more than we can count for sure. So here are more recent discoveries. Like there's been a lot, and I honestly can't keep up with the papers that are being written. But just to give you an idea of what we've discovered since the first images were released. So on the top left, you see Wolf Rayet 140. So the two stars, there is actually two stars. It's a binary system, and they produce shells of dust that look like rings every 8 years when their orbits actually come really close together. So it puts out a ring of dust. And this is because their stellar winds collide, compressing the gas and forming dust. This new study is going to it gives the best evidence so far that Wolf Rayet stars produce carbon-rich dust molecules. Even more cool, the preservation of these dust shells show that it can survive in the most hostile environment between stars, which eventually could supply material for future stars and planets. And then there's a cartwheel galaxy in the middle at the top. So using Webb's infrared technology, Webb captured this new image of the cartwheel galaxy and its two smaller companions that you can see on the left, with many other galaxies in the background, as you can see those sparkles in the background. And the image actually shows new detail about star formation and the galaxy's central black hole and how it changed over billions of years. Its appearance is the result of a high-speed collision between a large spiral galaxy and a smaller galaxy not visible in this image. Then there's the galaxy pair, VV191, which is really cool as well. And it shows two galaxies, and it's actually two images in one that are juxtaposed. So one is a near infrared image from Webb, which is, if you can see the green, yellow, and red in the image, that's Webb. And the other is an ultraviolet and visible image from Hubble, so the blue. Webb allowed researchers to trace light from the elliptical galaxy on the left through the spiral galaxy on the right. And by doing that, we're able to study the effects of interstellar dust in the spiral galaxy. It's important because understanding where dust is present in galaxies is going to allow us to understand the formation of new stars and new planets. Then there's the Tarantula Nebula. And this mosaic image, stretching 340 light years across, so it's really big, we have new information about the Tarantula Nebula, which is located, I believe, in the Large Magellanic Cloud galaxy. It's a star-forming region. We can see tens of thousands of never-before-seen young stars that were previously shrouded in cosmic dust. The most active region is shown in blue, and it almost sparkles with massive young stars. But why is that so interesting? Well, because it has a similar type of chemical composition as the gigantic star-forming regions observed during the universe's cosmic noon period, when the cosmos was only a few billion years old and star formation was at its peak. So it's a perfect comparison if we want to learn more about that. Then there's galaxy IC 5332. On the left is an image from Hubble in the visible and UV light, and you can see the dark regions of dust that separate the spiral arms. Webb on the right, though, is able to look through the dust in the mid-infrared light. You can see so many more stars. And although some stars shine brighter at different wavelengths, so some stars are clearer in Hubble's view, there's a lot more that are visible in the mid-infrared range. And taken together, these two views provide us a more complete understanding of galaxy IC 5332's structure and composition. Then there's Neptune, and I know there was a lot more images, but those are the ones that I could fit on my slide. So Neptune. So you can see three different images here of Neptune. So um, on the left is what is it? I can't remember which mission it was, but anyways, it looks invisible. It was observed in the visible light, and in the visible light, it actually looks blue because there's small amounts of methane gas in its atmosphere. And then Webb observed Neptune at near infrared wavelengths, and Neptune doesn't look so blue when you look on the right. It looks really shiny and beautiful. And this Webb's latest image of Webb. And it is the clearest one we've had in about 30 years, I think, 30 plus years. And it's our first time seeing it in infrared light. So in Webb's image, the one on the right, we can see a thin line of brightness around the planet's equator, which could be a sign of atmospheric circulation powering Neptune's winds and storms. And we actually also captured some rings and 7 of Neptune's 14 known moons. So super exciting. And for my last slide, and this is what I find really interesting because we really don't hear about it a lot. 25 years, 25 plus years in the making. Like, how does it all come together? It's such a cool mission. It's going to revolutionize the way we understand the universe, and it already is revolutionizing it. But it's been 25 years. Like, how did we get here? So the first step in any space mission, obviously, we don't create space missions just for the fun of creating them, although it is fun. But there's usually a need, right? So, as space professionals, we go to conferences, um, workshops, and we meet each other. We talk about the needs, and our scientists and researchers, they have current technology that they're using, and then they hit a point where the current technology, um, they can still discover things, but you know they realize that there's gaps to continue their research, right? So it could be they're missing a type of wavelength, or they need a high resolution. So there's a need. So that the scientists and government officials and the industries, we talk together during those events, those conferences, and those workshops, and we talk to each other, and then we propose new ideas, right? Well, maybe we could do this, maybe we could do that, and then surveys are delivered, right? So we'll get all together and plan the next 10 years of, or 20 years, 25 years, however many years we want to plan ahead. And it's community driven. And we produce documents like, for example, the decadal survey that NASA just produced. So that gives the government a sense of direction to be like, okay, well, this is what our community needs. This is what we plan to do in the next 25 years. Now let's see how much money we have together, which partners are interested in collaborating with us. And then we move forward. We prioritize which mission will have the largest impact. And then there's international collaboration after that. So, there are some space missions that space agencies will do on their own. Can't name, maybe like RadarSat, I think is just no, it's not even RadarSat has international partners, and I think most of the internet the space missions have international partners. So once we have a plan, a vision, a survey of some kind that's community driven, then we talk within governments, right, and industries, and we're like, okay, so who wants to contribute to this? Can your country provide any kind of specific hardware? Like, do you have any expertise? Canada, for example, we're good in optics, cryogenics. Like, there's different skills that we have here in Canada that is also elsewhere, but and robotics, we're really good in robotics. So there are specialized skills that are available in different countries within industries. So usually we'll reach out to the countries and we're like, hey, like, do you want to provide anything to this mission? And in return, we negotiate something, like in return, have observation time or whatever it may be. So again, governments will talk at workshops, meetings, conferences, and we'll figure out a plan and we'll collaborate together on who's going to build one. And this takes a few years, right? It's not like right away we know, like we have to go back and consult our industries. So we came back to Canada and we, did a request for information. Is there anybody interested in doing this kind of work? What can you provide? So we will consult our community again and see what we could provide. And then there's negotiations with the country that's leading, right? So then we negotiate. Can we have observation time? Can we have more observation time? Can we, it could be anything. Like we'll negotiate different things. So that can take quite a few years, actually, just to make sure that we know, okay, this is what we're going to build. This is what each country is going to contribute and which countries are going to collaborate. And then once that's done, we all go back to our separate ways, back to our countries. Then the project management starts. So once we've sort of agreed on something, then we need to prove to our government that this is a worthwhile investment. So we'll do a business case and we'll do like a risk analysis and we'll talk about all the stakeholders and the benefits of investing in space and what it'll bring for Canadian citizens. It'll bring jobs, it'll bring like increased expertise in a specific field, visibility, good relationships with our international partners, which will bring money back into Canada eventually, or every country does pretty much the same. And then once our business case is approved and we have a budget, a preliminary budget, then we'll start doing stuff like project management, right? So a project management plan, or we have a schedule, like this is how many years we're planning to take, this is our budget, these are the risks, and here's the work breakdown structure. And in the work breakdown structure, you say, well, we need to do this and this and this. So I have steps, and then you assign people to them. You're like, well, this person is responsible for this part of the work breakdown structure and this work pack, and this person is responsible for this work pack. Then you assign budgets to each. And then once you have your work breakdown structure and your project management plan is approved, and again, all of these things take at least 2 to 3 to 5 years. It takes a really long time. Sometimes you can do it in a shorter time frame. It really depends on how big the mission is. Then you do a request for proposal. So no contract is given to any industry or university or any entity without it being a competition. Like everybody has a fair chance in winning a contract. So we do a request for proposal. We'll receive all the proposals, we'll evaluate them, and then whoever wins gets the contract, right? So we had a contract to build FGS Nearest, and we had a contract to build the software that goes along with it with the university. And then along the way, things change, the scope changes. I think FGS Nearest was something else before. I can't remember what it was, but it actually changed. Like we were supposed to provide a completely different instrument, and halfway building it, we realized, oh, we need something else. So we actually changed it. So we had to do a change request, go again to the highest officials in government and say like, okay, we need to change it because of this, and these are the risks, but these are the benefits, and this is how much more money we're going to need. So there was actually a change request and probably a few change requests. And then, once everything is built, again, it takes a few years. You have to do lots of testing. It takes a long time, maybe 4 or 5 years. And then you do lots of testing to make sure that your hardware works, that it's going to survive the harsh environment of space. Then you bring everything together and all the pieces from different parts of the world, and then you build the puzzle and make the telescope or the science instrument that goes into space. And then you do more tests so that everything to make sure that nothing breaks. And then we tried to fold it and open it and fold it and open it. Okay, everything's working great. Along the way, we had a few problems where we had to ship pieces of the telescope back to the country and then bring it, fix it and then send it back. Sometimes they would send, things weren't working exactly the way they should have. So there's a lot of little hurdles that come along the way. And this is for any space mission and probably any project, even if it's not space related. There's unexpected things that happen. And that's why there were so many, not so many, but there were a few times where the launch was delayed and pushed back, because when you send something this big and this expensive into space, you want to make sure that it works and that it's not going to break down. And goes to show that it was good that we delayed the launch, because everything went pristinely well, and we're all super excited about that. And then once everything is done, And telescope sent into space, and then you do the commissioning for 6 months, where we opened all the different parts of the telescope. We turned everything on, tested everything. Then we start doing the ops transition. So we're transitioning into operations. And operations is when you're actually taking data and it's actually operating. So this is like the exciting part that we all waited for. And again, like even then with the operations transition, there's a lot of things to do. There, you need to close out report. You need to make sure that the operations contract is out, because you need people that build the hardware or somebody else that is capable of doing the work, operate the instrument, or at least do patches on the software. So again, another request for proposal, another open competition, another winner selected. So a lot of work there. And then there's the delivery, integration, and tests, which I spoke about earlier. Launch and commissioning, I talked about. Operations, and then the last point that I'm going to make is the research grants, right? Because obviously researchers, they applied for grants at NASA and SDSCI, the Space Telescope Science Institute in Baltimore. And like there's hundreds of proposals, right? So you have to be ready before operations begin. So this started like a year before launch, and there's hundreds of proposals, and they have to be peer reviewed to make sure that it sound science, and that it's going. They have to select a few people. They can't select everybody. There's not enough time in observation. So if I can just make a quick side note here, in operations, I was mentioning before that the solar panel powers a science instrument. Well, some space missions only have a set amount of power before it recharges. Like it needs to recharge to be able to acquire more data, right? So the research grants, let's say you can only observe for like I don't know, 600 hours a week. I don't know exactly what number it is. I'm just talking generally here. Then you need to plan accordingly. You need to use that 600 hours of observation time every week with really high efficiency, right? So you have to know which targets you're observing. They have to be targets that are going to be useful for a lot of different research. They have to advance science relatively well, not well, but like really good. And then you need to give enough time to downlink the data, right, on that power that you have left before it recharges. So the research grants actually got accepted before operations. Not the research grants, sorry, the observation time at NASA. The people that got observation time got selected, and then once they're selected, they can apply with us, depending on different organizations. So for Canada, we did an announcement of opportunity after we knew how many people had gotten observation time, and they were able to the researchers were able to apply with us to get research grants. And again, it's a second step of a competitive process. So they're again competing for funding. So there's only a set amount of funding, and we have to select X numbers according to our funding. So that's pretty much the whole story of how it all comes together. I hope that makes sense. And here are some resources and contact information in case you're interested to learn more about James Webb, or you have some media requests. Thank you.
Oh my goodness, Julie, thank you so much for this incredible look at how missions like the James Webb Space Telescope are realized. I've heard a rumor that there are a lot of questions in the YouTube chat. So I'm going to hand you over now to our RASC DDO Outreach Coordinator, Quentin Wayrich, who has been monitoring that chat for all of those questions. Over to you, Quentin.
Thank you so much, Denise. Yes, it is true. There are a lot of questions from the chat this time. Julie, that means the audience is absolutely loving what you have to say. They're very interested. So we're going to try to go through as many of them as we can. I guess we'll have to try to keep our answers fairly brief, so to make sure that we can get to everybody. The first question that I've got here is from Zapfan, who asks, has JWST observed any Kuiper Belt objects yet? I know that we observed the rings of Neptune. Do we have any plans to observe anything within the solar system beyond that?
There's been I don't know of any. It's probably going to happen at some point. Honestly, there was so many research proposals that were accepted. I don't know them all, but I don't honestly in this wave, because there's different waves, right? Right now, there's the cycle 1 and then there's cycle 2. So it's possible that in the other cycles we might have proposals to look at the Kuiper Belt, but I don't think right now there is. Don't quote me on that. I'm not sure. I don't know them all, but I haven't heard. I don't think I've heard that we're going to observe that. It's possible though. I may be wrong.
Yeah, I tried to do a little bit of research on it just to see if I could find anything, and it seems like there are definitely a lot of proposals, but I wasn't able to find any information about it happening yet. So stay tuned. It seems like they're going to try to do this. I don't know if they have yet though. Norm Hughes asks, does JWST have any visual type cameras on board besides all the scientific instruments? So is it just infrared cameras, or are there any visual light cameras?
It's just infrared.
Oh, wow.
It's in a different, there's mid-infrared, far infrared, but I don't know. It's just infrared.
Wow. Okay. They're really focusing on the infrared for this then. Awesome. Okay. We've got a question from Michaela Sabo, who is essentially talking about the very high redshift galaxies that the James Webb Space Telescope has been observing. She says, I watched a documentary talking about the Big Bang Theory being wrong due to finding galaxies with smooth, round edges. What's weird is that they're older than this theory. Any comments on that? And I did a little bit of research on this. I was able to find the oldest one I was able to find information on is called Glass Z13. I assume that's redshift 13.
Yeah.
And it's 300 million years younger than the Big Bang. So I wasn't able to find anything older than that. Did you find, like, this article came out in July. Do you know of anything that might have happened since then?
I haven't heard of anything since then. I have heard about that, and I was expecting the question, to be honest. No, it doesn't disprove the Big Bang. I'm going to say that clearly. It doesn't disprove the Big Bang theory. It just means that we're going to have to revise our simulations and our equations to make sure that they're correct. But no, it doesn't. It doesn't mean that the Big Bang is not the correct theory. At least not for now. We don't know in the future, but right now, no.
Excellent. Yeah, I figured like that would probably be front page news in like every science journal if we did end up disproving it. I have a question. I've got another question from Zapfan, who is from Sweden, and they're asking. There are European instruments on the JWST, but I don't know if any component of them were built in Sweden. Now I know that Sweden is a member state of the ESA. Do you know specifically if any of the components that the ESA contributed were built in Sweden?
I don't know, but it's 17 different countries, right? So likely, but I can't say for sure.
Fair enough. We have, okay, this one's a little bit more of a fun one. Norm Hughes asked, being just a 100-ish kilometer distance, I wonder if anyone on the ISS has been able to see Hubble, like a bright reflection. And I was really curious about this. The thing is that Hubble and the ISS are on different orbital inclinations.
Oh, that's true, yeah.
The Hubble is, I believe, at 28 degrees, and the ISS is 57 degrees. Is that your understanding as well?
I don't know the inclination. I'm not sure, but I know they're on different orbits.
Yeah. So it seems like it might be possible because they would intersect, and then they'd be. But the timing would have to be just right. So it seems like it'd actually be easier to observe them from Earth, even though you're further away when they're directly overhead.
Probably. I don't know what the inclination is or if they've ever observed it. It's a really good question. I'm curious.
It is a great question. We also have another question, another kind of fun question from Michaela Sabo. Could we eventually form our own small stars to produce our own energy on Earth? I think this is talking about nuclear fusion. So I know a little bit that we've attempted to generate energy through nuclear fusion before, but we haven't been able to make it produce more energy than it takes to run.
Yeah.
So if you've ever heard of, I know like there have been a bunch of attempts to create cold fusion, which is when you're able to generate fusion at lower temperatures, that it's more efficient to run. But I don't think we have that yet. If we ever do get there, that'll be big. That'll be very big.
I honestly, I haven't heard of anything. I've heard of quantum entanglement, quantum entangled particles being like, played with whatnot,
Yeah.
and
Well, that was the Nobel
but
Prize this year.
was it? I didn't follow.
Yes.
Was it? Oh wow. Okay, I'll go. Really? The
Yeah.
quantum entanglement thing? Oh
Yeah.
my gosh.
Yeah,
Awesome.
it was just awarded a couple weeks ago.
Yeah, it was good, but I didn't
this
check
week
it.
maybe.
Yeah, it's usually early October. I'll go check it out.
Yeah. I mean, if we ever discover cold fusion, I guarantee you that'll be another Nobel Prize.
Oh, absolutely. But no, I don't think it's done it. But I mean, I wouldn't put anything past humanity, right? Like, I mean, just look at how far we've come in the past 20 years. I mean,
Absolutely.
we're talking to our watches. That was Star Trek 20 years ago. So, but I don't think it's done now, like you said. But I wouldn't put it past humanity's capabilities.
We also did have we have been making pretty good time. We're almost through the questions, unless people have asked any more since I started. But we did actually have a question from Ras Toronto asking, how many targets a day does the JWST focus on? And I imagine that's kind of complicated, right? Because the research, like you get the hours to work on the JWST by grant, and everybody's going to have different projects, right?
Yeah. So
Yeah.
how many hours a day? How many targets a day? I mean, I know it depends on how much observation time you need, right? So some projects, small observation time, some project are larger observation times. I've heard of an entire morning being dedicated to one observation, and so far. And at Hubble, I've heard of an entire week being devoted to one observation. So, and it really depends on the project. But the projects are they're selected much ahead of time, right? So they already had time to build their observation schedule. I'm actually not privy to that information. I don't know how many per day, but I would say, I don't know, with my understanding of mission planning, I would say maybe 2 to 5 a day. I'm not sure, and it depends on the sky's availability. And again, it depends on how long you're observing, right? So
Right.
whoever got selected a year prior, the mission planners have been building, planning the observations since then. So they know what's coming next, which part of the sky is going to be visible, so sometimes I don't know how they do it for Webb, but yeah, it's got to be tricky, and it's probably been the acquisition plan, the data acquisition plan has probably already been done a while back, and I would say, yeah, maybe 2 to 5 a day, maybe. Again, I don't know. I don't have that information, but that's what my educated guess would be.
Fair enough. We actually do have some more questions in the chat since I last said that. Everybody's really interested in this talk. Melissa Miles asks, thanks for the presentation. Wondering what would happen if the telescope faced the sun. I imagine that would be a very bad idea, right?
Everything would die. No. I mean, no. Yeah.
I know.
My assumption would be they would not do, like, I mean, it's 85 degrees Celsius. I mean, that's hard. Like, try putting any electrical equipment near an 85 degrees Celsius heat source. I don't think that would be good.
You can destroy just a standard Earth-based telescope if you point it at the sun without using a proper solar filter. So with a really sensitive instrument like the JWST, that would be a terrible idea.
Yeah.
It would honestly probably melt or crack the mirrors, which would be very, I mean, we put so much work into building those.
What's the melting point of gold? I don't remember.
I don't know either. We have another question.
Sorry.
Oh, okay. Zapfan asks, do you know how fast the JWST can slew? How fast it can move from target to target?
Hey boy, I should know this. but I don't.
Fair enough.
I don't. I'm sorry. Oh no, wait, I do. See, wait, was it the I know, like, there's a speed. I'm not sure what speed it is, but I remember one of my colleagues saying that something moves like at the speed of grass is growing, but I don't remember what it was. Is it the way that? Do you remember? Do you remember hearing that, Quentin? I don't.
No,
Okay.
I'm sorry.
But I don't know if
The
it's like
slew rate has to be faster than that, right? Or we wouldn't
it
be
was.
able to get anything done with
Maybe it
it.
was some of the deployment of some of the instruments. I don't remember, but yeah, the
Okay.
I don't know. I really don't know. Sorry.
The and okay, this is a fun question. As of today, what has been the most exciting thing that JWST has discovered in your opinion? This is from Norm Hughes. What were you the most excited about?
I was really excited about the deep space image because I mean it's sort of like what my interests lie in, like cosmology and the grand scheme of things and how everything comes together. And when I saw how many galaxies there were, I was just like, this is terrifying. Just like terrifying because there's so many, and like it just, I don't know, it boggles my mind. And B, because when you look at deep space, you can really look at the beginning of things, and we assume certain theories like the Big Bang, for example, and no, it hasn't been disproven. But just think of all the different things that we could find out just looking at the beginning or close to the beginning of time, or even further than we think we can. um yeah, I'm really excited about that. That's my favorite. What's yours, Quentin?
I'm a big fan of Neptune's rings, just because it's really cool to see an object in our own solar system that we kind of feel like we understand already, kind of feels familiar, put into that new context where it's just completely new. It keeps reminding me that even the things that we think we understand, we don't really fully understand. It's a good reminder.
Absolutely. Yeah.
So I think that concludes the questions from the chat. Thank you so much. This has been an excellent talk.
Welcome. This has been a pleasure.
Have a great night.
Amazing. Thank you so much, Quentin, for relaying those great questions from our audience. And Julie, thank you so much for giving us these incredible insights into how this mission works, and also, of course, your reactions to it. Wonderful. We do have a little more on our program for you tonight. This would not be a DDO online event without, of course, a tour of the DDO. So we've prepared a short video tour for you. We will come back after this tour with a live view from the big scope. As you can see, it's dark in here now behind me, and I've bundled up. It's gotten cold and dark, and we have a great live view for you. So we'll come back after the video tour for a live view from the telescope, and to answer any questions that you might have about the DDO or the telescope. Over to the tour.
Hello and welcome to the David Dunlap Observatory. Behind me is Canada's largest optical telescope. My name is Denise Chilton, and I am a rascal, a member of the Royal Astronomical Society of Canada, Toronto Centre. It is my pleasure to be an operator for this telescope, and tonight I'm going to give you an inside look at this telescope and how it works. But first, let's think about the history of this scope. This facility opened in 1935. Originally, it was a research telescope for the University of Toronto. It was named in memory of David Dunlap, who had thought that he was going to provide some funding for the construction of this scope, but his unfortunate death prior to that funding being secured put the future of the scope in jeopardy. It's very lucky that his widow, Jessie Dunlap, came forward to donate the funds for this facility. The telescope was built by Grubb Parsons in England, in Newcastle-on-Tyne, in 1932 and 1933. It was shipped across the Atlantic in pieces after being completely built and assembled and then disassembled in England. It was shipped here and rebuilt on this site, and it opened in 1935. It was in use as research telescope for many years, but unfortunately, due to light pollution and the availability of bigger and better research telescope facilities, the University of Toronto closed this telescope in 2008, and the property was eventually sold to the city of Richmond Hill. The good news is that the telescope is now open for public tours. Unfortunately, with COVID, we can't have people in the building, but tonight it will be my pleasure to show you how this telescope works. So how does a telescope work? Well, a telescope points outside at the night sky. Light flows down the optical tube, light from moon or stars or planets or dark sky objects, and it's collected by the great big mirror behind me. This is the primary mirror in the telescope. In this case, this one is 74 inches across, or 1.88 meters. You can probably see my reflection back there behind me, and it's this diameter that makes this telescope so powerful at collecting light and at being able to see very distant objects. When this facility opened in 1935, this became Canada's largest optical telescope, taking that record from the Dominion Astrophysical Observatory in Victoria, British Columbia. Their mirror is only 72 inches in diameter. Rumor has it that when Dr. Clarence Chant, who commissioned this telescope, placed the order for this mirror, he asked specifically for it to be 2 inches bigger than the Dominion Astrophysical Observatory's telescope mirror, so that he could have the record of the largest telescope in Canada. When this opened, it was also the second largest telescope in the world. No longer the case, of course, as much larger optical telescopes have been created since then. To get back to how a telescope works, light flows in from the night sky outside. It is collected by this great big primary mirror and bounced back in that direction toward you. I'm not sure if you can see this contraption at the top end of the telescope here. This is the secondary mirror attached to these vanes. The secondary mirror collects the light from this primary mirror and sends it back down the telescope to the hole in the very center of the mirror. This hole leads to an eyepiece down below, and that's where you, if you were here, could come and look through the telescope and see distant planets, distant stars, or dark sky objects. You might have noticed that the sun rises in the east and sets in the west. If you were to stay up all night, you might notice that all of the objects in the night sky do the same. The moon, the stars, the planets, and more. This is because the Earth is rotating. But what this means is that the telescope needs to be able to lock on to night sky objects and then track them across the sky as the Earth rotates. So we have some controls over here that allow us to lock onto our targets. Every object in the night sky has a set of coordinates. We call these coordinates right ascension for east to west and declination for north to south. These are the same as latitude and longitude coordinates for objects on Earth. Let me show you how our controllers work. This is our declination controller. It helps the telescope move north to south. Let's watch how that works. As the telescope is moving north, we can see the coordinates in the counterweight on the other side of the telescope, so we know exactly where it's pointed. Now that we have our declination coordinates locked in, north to south, we're going to lock in our right ascension coordinates, east to west. We use this wheel to do that. First, we unlock the telescope. And then we can turn the wheel, and our coordinate system is up here on the setting circle so that you can see pointed in the correct direction, we need to lock it in place again so that it doesn't swing around. But you might have noticed that the telescope is no longer pointing at the open sky. Instead, it's pointing at the inside of the dome. So we need to rotate the dome roof to bring the open window in front of the end of the telescope. The dome weighs 80 tons. It rotates on a set of 24 train wheels connected to a cable and pulley system powered by a motor downstairs. Once the open shutters are in position, we're ready to start observing the night sky. Just up this ladder, we can find our way to the eyepiece. I wonder what I'll see tonight. Thanks for joining us for this virtual tour of the David Dunlap Observatory. We hope to see you here in person as soon as we're able to reopen the facility for public tours. Until then, wishing you clear skies.
So I hope you enjoyed that tour of the facility and that this glimpse inspires you to visit the DDO soon to learn more about the facility and its rich research history. I will say that the DDO facility has now fully reopened to the public, and we are looking forward to hosting in-person events again soon. With the weather getting colder, though, those will be few and far between, probably until next spring. But stay tuned for more online events for sure. If that tour is not enough to get you interested in visiting, we do have a live view tonight for you. So I believe we're going to cut over to the camera now. The camera is mounted to the eyepiece position of the DDO telescope, the 74-inch or 1.88 meter telescope. And I will give you one guess which planet this is. That's right, it is Jupiter. Jupiter is the largest planet in the solar system. It is the most massive planet in the solar system as well, containing about twice as much matter, actually, sorry, more than twice as much matter as all of the other planets combined. In the diameter of Jupiter, I think you can fit 13 Earth diameters going across the diameter of the planet. So that gives you an idea of how huge it is. Now, it's also very different from Earth because, of course, it is a gas giant. So it is composed mostly of liquid and gaseous hydrogen and has no solid surface. So again, that's Jupiter. We can see some great cloud bands in this image. I know it's a little bit fuzzy. We are having some upper atmospheric movement, and you can see that the image does bounce around a little bit. That is typical of live views from ground-based telescopes. So you can see some cloud bands. Now, I know that later tonight, actually, very early tomorrow morning, we should be seeing a transit of the Great Red Spot. So that's the great big storm that's been going on for hundreds of years on the surface of Jupiter. And that is scheduled to make an appearance after midnight tonight, so in the early hours of Saturday morning. So if you're staying up late and you have your own telescope, hop on out there and take a look. So we're going to head over now to our outreach coordinator, Quentin Wayrich, to answer any questions that you might have about the David Dunlap Observatory or the 1.88 meter telescope. Quentin, are people asking questions in the YouTube chat?
We have a question from ZapFan about the telescope.
Perfect.
They ask, have you had to make any spare parts for the telescope over the years?
Yeah, so actually just recently, I'm trying to remember, it was in the spring. I think it was in the spring. We had a problem with the focuser. One of the gears had its teeth sort of stripped just from years and years of, of use. So what we ended up doing was having a gear specially machined. So they took the measurements based on the gear that was there, and they were able to create and replace that part. So yes, it does happen, but it often involves having custom parts created because, again, This is it's an antique. It's a part of our Richmond Hill heritage, and it definitely, it's one of a kind.
Norm Hughes asks, do you guide the telescope, and if so, how?
Okay. So that's a great question. As we saw in the tour video, the guidance of the telescope involves setting the coordinates for right ascension and declination. It has a very small motor, about the size of a washing machine motor, that then compensates for the Earth's rotation. So the only thing that the telescope does is basically move east to west to follow the sky, right, as the stars move across the sky. And so it's just one little motor that allows it to do that. The rest of the guidance is done manually by setting in those coordinates.
We have a couple questions from Michaela Sabo. First of all, how far does the telescope see? That's a great question. And also, do you have local programs for inspired youth to learn about space?
Okay, these are two great questions. So I'm going to answer the first one, then you're going to remind me of the second one. So how far does the telescope see? This is a difficult question to answer in the sense that the magnification of the telescope does allow us to see into some of the deep reaches of space. We can, in theory, see very, very distant objects, hundreds, thousands of light years away. However, this telescope is limited by the fact that there is a lot of interference. So we are in an area where we get cloudy skies a lot, not perfectly clear skies. We're down low, close to sea level, which means there's a lot of atmosphere above us and there's a lot of atmospheric interference. Anytime the wind blows up in the jet stream, it disturbs the image. So the dimmer the object you're looking at, the harder it is to see in those conditions because it's moving around a lot. I mean, even with Jupiter, we saw a little bit of bouncing around there. And that's a very close, very bright object. So, it's exponentially more difficult to acquire a distant target and see it clearly from, given that we are down close to sea level and that often we have atmospheric interference, either in the form of outright cloud or just like light haze and high winds that sort of mess with the viewing. The other interference that we see a lot of, and of course it's getting worse, is light pollution. Ground-based light does limit what we can see in the distance. So this is why, as much as I would love to give you a firm number of, we can see X many light years, it's really hard to say that for sure because it will depend on the night, on the seeing conditions, on whether the power is out locally, although that would limit our telescope severely because it does use power. What was that second question again? It was about youth programs, is that right?
Yeah, specifically though, it turns out that Michaela is asking about programs in Kitchener-Waterloo, where I assume they live.
Okay.
Now, does the RASC have activities out there?
So there should be a local branch of RASC. I'm not 100% familiar with all of the different RASC centers, but I know, we have one here in Toronto, and then there's another one next door in Pickering. So they are pretty common across Canada. RASC is the Royal Astronomical Society of Canada. It's a national organization, and there are centers across the country. So I would I'm hearing, sorry, from our tech director that in fact, Kitchener-Waterloo does have a RASC center. So I would say Google that, look that up, and see what programs they offer. Because I can tell you with 100% certainty that here in Toronto, yes, we have all kinds of youth programs. A lot of them are centered around when students have time off. So I was just talking to Quinton the other day about planning already for our own March break programming here at the DDO. So that's the sort of thing that RASC centers are doing across Canada. So definitely check with your local RASC center and see what they have on their schedule.
All right. How much more time do we have? We're still getting questions.
We have time for a few more questions, Quinton. Lay them on me.
Does the telescope have certain filters to make images better? I don't believe it does it?
That's a great question. So there is nothing prohibiting us from using filters with the telescope because most filters for astronomy are at the eyepiece. So as long as you can fit them into your eyepiece, they screw into the eyepiece, then we can use those filters. Currently, we are not using any filters. So that image that you saw of Jupiter was completely unfiltered. Arguably, we could probably use a planetary filter and get a clearer, crisper image. So maybe that's something we'll have to try at some point.
Thank you. Melissa Miles also asked, my daughter Maya would like to know how often you can see Jupiter's Great Red Spot. And Zapfan mentioned that Jupiter orbits once every 10 hours. Now,
Yeah.
you wouldn't need a big telescope like we have to see the Great Red Spot, right? You could do that with a backyard telescope, correct?
You absolutely can. A 6-inch telescope will easily help resolve the Great Red Spot on Jupiter. And as Quentin was saying, every 10 hours, Jupiter revolves on its own axis. So we see that, technically we see it coming by every 10 hours. However, it's really hard to see in the daytime. So if the Great Red Spot is facing us and it's daytime for us, that's going to be really more difficult to observe. So what we have to do is look for those coincidences where it's nighttime here and we have good clear skies and the Great Red Spot happens to be going across. Yeah.
All right. I believe that we have come to the end of the questions now. Thank you so much, Denise.
Can I add to that? I wanted to also say that Jupiter is approaching its opposition. I think it's in November, right at the start of the month. So this is peak Jupiter observation season. Like right now is a great time to get out there. Jupiter is rising just after the sun sets and it's up for much of the night. So the best opportunities to see that Great Red Spot are now when Jupiter is up all night long.
All right. Thank you.
Okay. So thanks, Quentin, for all those questions. Thanks to the audience members for sending in all those questions. We really appreciate it. On behalf of the Royal Astronomical Society of Canada Toronto Centre and the RASC DDO Committee, I'd really once again love to thank Julie Claveau for sharing these amazing insights into launching space research missions. It's been really incredible to hear from her tonight. Thanks also to our technical support team, Andrew Reed and Betty Reed, and to my technical support team over here, I have James Chilton helping me with the big telescope. Thank you, Quentin Wayrich, for fielding questions from the YouTube audience. And of course, a special thank you to all of our viewers for joining us this evening and for sending in such wonderful questions throughout the course of this program. This talk has been part of our 2022 season of astronomy events at the David Dunlap Observatory Online, offered through the partnership of the Royal Astronomical Society of Canada Toronto Centre and the City of Richmond Hill. We do have some upcoming events that you might be interested in. On November 6th, we have Ask an Astronomer. This may or may not be happening in person. We are currently looking at the transition from virtual events to in-person events, so we're going to be assessing that possibility. That's again on November 6th. On November 12th, we have another astronomy speakers night coming up, so join us again for a talk from an expert, from an astronomer or somebody working in the space research industry who will tell us all about their area of expertise. On November 13th, Sunday, we have a Sunday sun gazing event. This is where we pull out our own RASC member telescopes with appropriate solar filters and give viewers live views of the sun, hopefully, if the skies are clear. We do include pre-recorded views if the skies are cloudy, and we will give you all kinds of great information about our nearest star. Finally, on December 2nd, we have an Up in the Sky event planned. Once again, this is where RASC members pull out their telescopes, this time pointing at night sky objects, and we live stream those for you. And of course, if the weather is clear, we like to come over here to the DDO and pull up a few targets on the big scope as well. All of these events and more are posted on our website, rascto.ca. So please do have a look there for more details. We're very much hoping that you are as excited about astronomy as we are and would love to try it for yourself. So to wrap up this evening, we have some tips to help you. Please enjoy this video on getting started in astronomy. Wishing you a wonderful night and clear autumn skies.
A question we're often asked is, how do I get started in astronomy? It's a really great hobby, especially in this COVID context. It gets you outside for fresh air, you don't need to do it in a group, and there are tons of free resources online. So here's a quick guide to getting started in astronomy. Step 1 is to learn the sky. This really is essential, as it's important to be able to orient yourself and know what you're looking at. There are lots of resources to help you with this. If you prefer books, I can recommend Night Watch by Terence Dickinson or The Beginner's Observing Guide by Leo Enright. Or if you'd like to print out some star maps and star finders, there is the Star Finder from the Royal Astronomical Society of Canada. That's a printable star finder that you can take out with you under the night sky. Or you can print sky maps and sky atlases from skymaps.com. If you're a little more tech savvy and you prefer programs and apps, I recommend Stellarium. This is free planetarium software you can install on your home computer. Or Sky Safari. This is an excellent app for your phone. Once you've got your bearings, step 2 is to start observing. That's right, just head out under the night sky and look up. You don't need any special equipment, just your eyes. With your eyes, you can see things like constellations and asterisms. These are the formal and informal patterns that stars make in the night sky. You can see planets like Mars and several other planets as well. You can see the moon and observe its different phases as it moves across the sky. You can see meteor showers, comets, and even one galaxy that's bright enough to see with your naked eyes in a very dark sky area. Maybe you're inspired to look for more than what you can just see with your naked eyes. So step 3 is it's time to start collecting some gear. Now, you might be surprised that you may already have some of the things you need lying around the house. If you have a pair of binoculars, you can point those at the stars. If you don't, they're a small investment with a lot of benefits. With binoculars, you can see details like craters on the moon, or the phases of Venus and the moons of the planet Jupiter. You can even see smaller, fainter asterisms and double stars. Remember, one of our famous astronomers in history, Galileo, started out by using a telescope that didn't have much more magnifying power than an average pair of binoculars. His contributions to astronomy are remarkable, and you can see a lot through your binoculars too. If you're ready to get a little more serious about your astronomy hobby, you might consider investing in a telescope. A small amateur telescope is a big investment, but with more magnification possible, you can see more detail on the surface of planets, the moon's craters, you can see many double stars, some galaxies, and nebulas, and other deep sky objects. I recommend joining the Royal Astronomical Society of Canada to participate in the Telescope Loan Program if you're interested in buying a telescope. You'll have an opportunity to try out many different scopes and determine which one is best for you. And this brings us to step 4, connect to a community. You can find information about the Royal Astronomical Society of Canada Toronto Centre online at rascto.ca. And through RASC, you can learn about upcoming astronomy events, you can find more astronomy resources, and you can become a member of the club for additional benefits, like that telescope loan program I mentioned. I hope this guide has helped you to feel confident in getting started in astronomy. Enjoy those clear night skies.